Okay, let us start. So we started with the Lyapunov's direct method, and in this method we are using some auxiliary functions in order to be able to decide whether equilibrium points of nonlinear systems are actually stable or unstable. So here, these functions are energy-like functions for a system. So these functions are shown as v of x, and they're going to satisfy some properties. So we are assuming that our system is x star is equal to f of x, and our system has an equilibrium point at 0. So we are assuming that the equilibrium point is at the origin. If it's not at the origin, we could always transfer it into the origin by defining a new state variable z. And in that case, the new state equation in terms of the z variable will have an equilibrium point at z equals to 0. So here, therefore, these energy-like functions are defined around equilibrium point 0. And they are therefore always defined as being equal to 0 at the origin. So this function is going to be usually a ball-like function, and it is going to be exactly equal to 0 at the equilibrium point of the system. And depending on what happens at other places than the origin, we classify such a function. For example, we say that the function is locally positive definite sometimes, and sometimes we call it globally positive definite. It is locally positive definite if and only if there exists a ball BR such that in this BR, this function is actually strictly larger than 0 for any x inside BR minus the origin. That is local positive definite. So around the origin, we look for a ball with non-zero radius, a positive radius, such that the function is positive everywhere in that ball except at the origin. Okay? We say that the function is actually globally positive definite if we can make this ball infinitely large. So in that case, function is called globally positive definite if and only if. So we have v of x is positive for any non-zero x. Okay? In that case, we could make this local BR ball infinitely large. So we have also some local positive semi-definiteness and global positive semi-definiteness definition. We say that the function is locally positive semi-definite or globally positive semi-definite based on some properties. Locally positive semi-definite function for such functions, there exists a BR such that v of x is larger than or equal to 0 for any x inside BR. Okay, that is what we have. And globally positive semi-definite functions, we could make this BR ball as large as possible, infinitely large. So in that case, a function is called globally positive semi-definite if and only if v of x is larger than or equal to 0 for all x in the ball state space. Okay? These were the definitions of the function properties that we are going to be using. Remember, we could define similarly negative definiteness or negative semi-definiteness if we replace these greater than signs by smaller than signs. In that case, we would have negative semi-definite or negative definite functions locally or globally. Remember, we will be using these functions in the determination of stability properties of equilibrium points. So I have x1 and x2 here, and this function around the origin, it is going to have a ball-like structure. Okay? And then we will look at the trajectories of the system, and on the trajectory of the system, we will try to understand what happens to this function v of x. This function v of x would always have closed level curves around the origin. their shape might be different than ellipsoids in general, but we would like this function v, to have closed level curves around the equilibrium point. In that case, we will be able to say that if here this is increasing v direction, increasing v direction. So if on the trajectories of this system, if v is always decreasing, we will be able to say that the equilibrium point of the system is actually asymptotically stable. On the other hand, we will be able to say that equilibrium point is stable if the trajectory, if v is non-increasing actually on the trajectories of the system. And in order to be able to determine that, we will always be looking at this quantity v dot, which is the total derivative of v with respect to t. So here, v is going to be a function of x1 and x2, or however many state variables we have, and then we will calculate v dot, and it's going to be del v over del x1 times this x1 dot plus del v over del x2 times x2 dot. In the general case, when we have x dot is equal to f of x, so here I could actually define the gradient of v as the following vector. The gradient of v with respect to x is going to be the following vector: del v over del x1, del v over del x2, going until del v over del x n here. If I have an n-dimensional system, in that case, that is going to be my gradient, which is a vector. Okay. In that case, such a quantity can be written in terms of the gradient as follows: the v, I will have transpose of it times x dot, which is going to be this function f. Okay, that is going to be nothing but this v dot, and based on the sign of this quantity, whether it's positive or negative, etc., we will be able to decide whether the equilibrium point is stable or not. So we are actually ready at this point to write our first theorem in Lyapunov's direct method. Let us write the theorem. This is a local stability theorem. Consider the system. X dot is equal to f of x with f of 0 is equal to 0, meaning that there is an equilibrium point at the origin. If in a ball BR around the origin there exists a continuous scalar valued function v of x with continuous partial derivatives. So we do not only want the function to be continuous, we want its partial derivatives to be continuous as well. Because we will be saying something about v dot, positive definiteness, negative definiteness, etc. So these positive definiteness these properties are defined for continuous functions. So we want v dot to be a continuous function as well. That is why we, in addition to the continuity of v, we would like its derivatives to be continuous functions. Okay? Continuous derivatives such that there are two properties. V of x is locally positive definite. I will just write PD here in BR. And V dot of x is locally negative semi-definite in BR. then the equilibrium point xc is equal to 0 is stable in the sense of the epsilon. Okay? This is the first conclusion of the Lyapunov's direct method. If we can find a function and if we can find a ball around the equilibrium point, if that function is locally positive definite, and if its derivative with respect to time, if it is rate of change on the trajectories of the system, if it is locally negative semi-definite, and in that case, we will be able to say that the equilibrium point xc is equal to 0 is actually stable in the sense of the Lyapunov. There is a second and stronger conclusion of the theorem if another condition is satisfied. If v dot of x is instead locally negative definite, so not only negative semi-definite, but we have local negative definites, then the equilibrium point xc is equal to 0 is locally asymptotically stable. In this case, we can not only say it is locally stable, we can even claim the asymptotic stability as well. Is locally asymptotically stable in the sense of the. This is quite natural because here, if v is not increasing, then we will be able to say that the trajectories are never going towards outside these level curves. Okay? If v is not increasing, that means that I know that the trajectories are never getting away from the equilibrium point. They are either wandering on these level curves or they are going towards inside. Since the Lyapunov stability, in an intuitive sense, it is non-divergence of the trajectories. When v dot is actually non-positive, in that case we can claim stability of the equilibrium point. On the other hand, if v dot is if it is strictly negative all the times, in such a case we know that the trajectories are always converging towards the equilibrium point, because v then should actually decrease. So if v dot is strictly negative everywhere other than 0 in a ball around the origin, then in that case we would know that we can find a ball around the origin in which the trajectories would actually converge to the equilibrium point. Okay, so we have two conclusions from this theorem. The first thing is when v dot is non-positive. If it is non-positive, meaning that v dot is actually smaller than or equal to 0, inside a ball around origin, in that case we will be able to claim stability, claim stable equilibrium point. Okay? In this case, we will not be able to say anything about the asymptotic stability. Okay? So in this case, if the function is not a negative definite, this is negative semi-definiteness. In this case, we won't be able to say anything about asymptotic stability. The equilibrium point can still be asymptotically stable, or it might not be asymptotically stable. We won't know by looking at it, looking at v dot. On the other hand, if v dot is strictly negative, in that case, we will be able to claim asymptotic stability. Stable equilibrium point. Okay. In this case, that is what we can claim. So now we are actually ready for some examples. Let us look at it. Suppose that we have a second order system we have x1 dot is equal to x2 as the first equation, and the second equation is x2 dot is equal to minus x1 plus x2 cubed minus x2. Okay? This is the system dynamics, and we have to investigate stability of xc is equal to 0, 0 using Lyapunov function. V of x is equal to x1 squared plus x2 squared with Lyapunov's direct method. So when these V functions are actually used in the investigation of stability of equilibrium points, they are called Lyapunov functions. Okay? Ne çalıyor sizce? Anlayabiliyor musunuz? Bu stat'tan mı geliyor, Sevimtan'dan mı geliyor? So here we have this problem. It's a basic problem in terms of Lyapunov stability. The Lyapunov function is provided to us, and it is almost always going to be provided in this course. So we will investigate what we can say using Lyapunov's direct method about the stability of the equilibrium point. So here I'm going to look at V dot. V dot is going to be, I will take the derivative of this function. So first of all, let us try to determine the property of V. V of x is equal to x1 squared plus x2 squared. What is the property of this function in terms of positive, negative definiteness or semi-definiteness? So in this case, I see that this function is actually 0 at the equilibrium point. So it satisfies that property, and it is positive everywhere else. Okay? So, and it is continuous, it is positive everywhere else, meaning that this function V is globally positive definite. Okay? It's a globally positive definite function. Does it satisfy the property of the theorem? Does it satisfy the property that is required in the theorem? The theorem requires V to be locally positive definite, but this is globally positive definite. So do you think this doesn't satisfy the property of the theorem? Any globally positive definite function is at the same time locally positive definite. Okay, so global properties would always imply local properties. Okay, that means that there is an implication going from global properties to local properties. Similarly, positive definiteness would imply positive semi-definiteness as well. It's a positive semi-definiteness is actually a weaker relationship. All right. So here, there is V is globally positive definite. That is, therefore, V is also at the same time locally positive definite. Okay. That means that V is actually satisfying the property that is required in the theorem. Now we are actually ready to look at the property of V dot. And for that purpose, we are going to calculate what V dot is. V dot is going to be derivative of the function with respect to x1. It is going to be 2x1 times x1 dot. x1 dot is x2. Okay? So I'm actually doing this calculation. This one is 2x1 times x1 dot is x2. And I will sum this with derivative of the function with respect to x2. We have 2x2 times x2 dot. That is going to bring me that term. Minus x1 plus x2 cubed minus x2. Okay? That is what I have. And here I see that these terms are actually cancelled here. So I'm going to get the following terms. 2x2 to the 4 minus 2x2 squared. Okay? So now what can we say about the property of such a function. In general, taking a negative quantities, quantities parentheses would be useful here. So here what I'm going to do is that I will take the parentheses of minus 2x2 squared. Okay? So this term is going to give me 1, and here minus, I will have x2 squared here in the parentheses. Okay? By looking at this form of this function, I can easily say what this function is in terms of positiveness or negativeness. Suppose that we are in a suppose that we constrain ourselves into a small ball around the origin. Okay? Suppose that the radius of the ball is smaller than 1. Okay? If the radius of the ball is smaller than 1, I know that this term would always be positive. Okay? So this is going to be always positive, meaning that the function sign is going to be determined by this term in that ball. Okay? So I can find a small ball around the origin in which the sign is this thing is always going to be positive and the sign is going to be always negative, or the v dot is going to be 0. Okay? So in a small ball around the origin, what can you say about the sign of this function? It is going to be negative in many places, and it is going to be 0 at the origin. The question is to determine whether it's negative semi-definite or negative definite. I need to check if this function can take 0 values other than the origin in this ball. So do you think this function can take 0 value anywhere other than the origin in this ball? So in a small ball around the origin, which radius smaller than 1, do you think this function can take 0 value anywhere other than the origin? Yes, if x2 is equal to 0, for example, at this point, which is not the origin, the function can actually take 0 value. So that actually means that the only thing that I can say about v dot is that it's going to be smaller than or equal to 0 in this small ball around the origin. Okay? So I won't be able to claim negative definiteness because the function can take 0 values in that small ball at other places than the origin. So here I can actually say that v dot is locally because I cannot make this ball indefinitely large. So if I make this ball have radius larger than 1, in that case the function sign can be actually positive. Okay? So therefore this is a local property. This is locally negative semi-definite. That is what we can say about this function. And now this actually means that the equilibrium point, by the conclusions of the Lyapunov's direct method, in that case, is x is equal to 0, is stable in the sense of Lyapunov. So all of the trajectories are non-diverging in a small ball around the origin. So this is a local stability result because we only asked for local properties here. Okay? Later in the second part of this lecture, we will also get a global stability theorem, and in that case we will ask these properties to hold globally. Okay? In that case, when they hold globally, if some additional condition is satisfied, we will see that we will be able to say global asymptotic stability and stability. Yes.
It is negative semi-definite.
Yes.
But if it started anywhere but the equilibrium point itself, it goes to the equilibrium point. So do we call it locally stable?
What do you mean? So here on this line, actually we have the function v dot is equal to 0. Okay? On this line, v dot is equal to 0. So if I start the system here, I am not sure what is going to happen to the trajectory. It might still remain still remain at this point, or it might move on this line. So sometimes some additional results can be actually extracted. Whether the system dynamics would allow the system to remain on this line or not. If the system dynamics does not allow the system to remain on this line, sometimes you can claim asymptotic stability for the system as well. But those have some separate theorems. They are called LaSalle principle in Lyapunov stability theory, which is not included in this theorem. Okay. Currently, we can only claim stability only, and we will not be able to claim asymptotic stability. So, what am I going to say? This equilibrium point is not asymptotically stable. Is it right? We don't know. So the theorem condition is not satisfied. This doesn't mean that it is not asymptotically stable. Theorem just states something P implies Q. When P is not true, this doesn't mean anything. Okay? So that actually means that this equilibrium point can be asymptotically stable. It might not be asymptotically stable. I won't know by looking at this theorem. Okay? So this doesn't, the result that we obtained does not say anything about asymptotic stability of the equilibrium point. But we can conclude that it is stable, but no result related to asymptotic stability.
So what happens if P dot is closely negative?
In that case, we can say asymptotic stable. The second part of the theorem is saying that if V dot is instead locally negative definite, if the function was locally negative definite, then we can say that the equilibrium point is asymptotically stable. Okay? So the theorem has two parts. In the first part, it says that if V dot is negative semi-definite, local stability can be claimed. But in that case, there is no claim about asymptotic stability. If V dot, instead of being only negative semi-definite, if in addition to that, if it is negative definite, then we can claim asymptotic stability as well. But for this example, there is no such claim because there is not negative definiteness. So here, let us look at another example. This is a hypothetical example that will illustrate a wrong conclusion for the theorem. So here, suppose that we have the following system: x dot is equal to f of x, and let us say that f of 0 is equal to 0. This means that the equilibrium point, there is an equilibrium point at the origin. Suppose that I started with a function. Suppose that I chose a function v of x. Let us say that it is positive definite. Okay? Let us say that we started with a positive definite function. Global or local, it does not matter for the sake of this example. And let us say that we get v dot of x. At the end of, we calculated it using this methodology. And let us say that we have obtained this, x1 minus x2. Okay? Let us say that v dot turned out to be this. In that case, what is our conclusion about the stability of the equilibrium point? So, what is the property of this V dot? Do you think it has some sign-definite properties? In any ball that is arbitrarily small, this function V dot is going to have mixed signs. Okay, so it's going to be positive, negative. Its sign is going to change in any ball around the equilibrium point. Okay, that actually means that V dot is actually an indefinite function. Okay, so there is no conclusion. So what am I going to claim then about the stability of the equilibrium point? It's unstable. Is it going to be my conclusion? This example is just, I covered this example just to say that it's the wrong conclusion. I won't be able to say anything about the stability of the equilibrium point. Okay? This is a theorem in terms of P implies Q. If the conditions hold, then we can claim stability. If the conditions do not hold, that means that your V is useless to claim anything. Okay? So in this case, the theorem is inconclusive, and I will not be able to say anything about the stability of the equilibrium point using Lyapunov's direct method. Okay? So in this case, we have no conclusion using Lyapunov's indirect method. Sorry, indirect. About the stability of the equilibrium point. I won't be able to say unstable. Okay? That doesn't make any sense. So let us look at another example. So this is the pendulum example that we have seen many times. So this is the pendulum system that I will consider. Does this pendulum have friction? Do you see it from these equations? Does this pendulum have friction? After some point, some strange thing happens to a human being. When we see differential equations, we start to see systems behind that. And when I see such a differential equation, I see a pendulum. Because I don't know if it's a good thing or bad thing, but when you look at this equation, you would understand that maybe for the rest of your lives, hopefully, you would see that this is actually a pendulum. But is it a pendulum with friction or not? Sorry? Yes. What is this term for? What is sin x? It's for the gravity. Okay? That's the gravitational force. What is this? That is the friction. Yes, exactly. So this is coming from friction. Okay? Because x2 is theta dot, and this is some constant times theta dot. This is the friction. Okay? This first equation is nothing but the relationship between the state variables. The first variable is theta. The second variable is theta dot. Okay? The first equation is the relationship between two state variables, and the second equation is the Newton's second law. Okay? This is theta double dot dot. This is theta dot. This is theta dot dot, which is theta double dot. Okay? So this is nothing but Newton's second law. This is the gravitational force, and this is the friction torque. Okay? So here, this is a pendulum with friction. So what is your conclusion about the downward equilibrium point stability? So is that downward equilibrium point, is it stable? Yes. Is it asymptotically stable? Locally asymptotically stable? So do you think the trajectories would converge? If I start the pendulum in a small region around that equilibrium point, do you think that trajectories would converge to the equilibrium point? Yes, it is locally asymptotically stable. That is our physical intuition about the downward equilibrium point. It's not globally asymptotically stable, but it is locally asymptotically stable. We can find an initial condition ball around the downward equilibrium point for which convergence is going to take place. Okay? So here we are to investigate the stability of the downward equilibrium point. So again, we are concentrating on the downward equilibrium point 0, 0, and we're going to be using the following Lyapunov function: 1 minus cosine x1 plus x2 squared divided by 2. Okay. So such a function is taken from the physical interpretation of a pendulum. Okay. So here we know that the pendulum is actually, let us try to draw it. It is looking like this, and this is x1 is equal to theta. Okay? So here, when you look at x1 is theta, and when you take x2 is theta dot, this is actually looking like the kinetic energy of the pendulum. This is theta dot squared divided by 2. Okay, this is like a form of kinetic energy for the pendulum, and this is in that case representing the potential energy. How does that do it? So it is the following case. Suppose that the pendulum length is actually, let us say that the pendulum has length L. Okay, let us say if the pendulum was vertical, let us say that in that case the pendulum length is L, and this length is also L. Okay? So in this case we will assume that L is equal to 1, but let us try to see that. So in that case, what can I say about this length? So what is the length of this part? It is L times cosine theta, actually. Okay, so this is L. The angle here is theta. So this length is going to be L times cosine. Okay, L times cosine theta. So in that case, you can actually say something about the remaining length. Okay, what is this length in that case? It is L minus L cosine theta. Okay, so the height of the pendulum in that case is going to be L times 1 minus cosine theta. Okay, so we would see that the height that the pendulum is at is described by a formula like 1 minus cosine theta, and we know that the potential energy of the pendulum is going to be proportional to this thing. Okay. So here in this Lyapunov function, it is actually coming from a physical interpretation of this system. This is a form of potential energy, and this is a form of kinetic energy, and their sum is the total energy in the pendulum system. Sorry? Yes. Yes, usually they will be given to you either in its explicit form, or it might be dependent on some parameters, and you might need to check. You might need to set those parameters to be able to use it in stability investigation. In this course, the Lyapunov functions will be given to you either in its explicit form with all parameters known, or they're going to be dependent on some parameters. Then what you have to do is that you need to set the parameters to be able to use that function in order to be able to investigate the stability of an equilibrium point. So here, actually, this is we will be talking about this. The weak point of Lyapunov stability analysis is actually the fact that function is never available in practice. You're going to get a nonlinear system. You will know its equations. You don't want to. You would like to prove its stability, but you won't know the Lyapunov function right away. Okay, so that is why that is a weak point of the theory here. We don't know these functions in general. We are in this course. We are learning how to interpret the results using these functions, but in practice, you won't know those functions, so you have to discover those functions yourself. So you have to use some additional methods in order to be able to derive those. That is the weak point of this theory. In some way, we are passing the problem of proving stability into the problem of finding a function that is going to be used for this purpose. Okay, we are replacing one problem with another, but once you know the function, you can solve the stability. So here let us actually try to use this function in order to be able to look at the stability of the downward equilibrium point. So I'm going to calculate again V dot here. V dot is going to be derivative of the. So first of all, let us investigate the property of this function. Okay, Is it positive definite, locally or globally? Let us try to understand. So first of all, I know that cosine takes values between -1 and +1. That means that this function is this part of the function is always larger than or equal to 0. Okay? It is either 0 or it is positive. And I know that this part is also larger than or equal to 0. Okay? So if anything, this function is going to be either positive definite or positive semi-definite. Okay? Let us try to understand when such a function is actually exactly equal to 0. If this function is equal to 0, in that case, both of these terms should be equal to 0. Okay? Because these are non-negative terms. And if the function value is equal to 0, if v of x is equal to 0, then both of these terms should be 0. Because if any one of them are positive, the function will have positive value. Okay? Well, it actually means that if v of x is equal to 0, we will have cosine x1 is equal to 1, and then x2 is equal to 0. Because these function being equal to 0 implies that these two equations are satisfied. Okay? So in this case, I can actually say that x1 is going to be a multiple of 2 pi. Okay? 2 pi. So where are these functions, where are the values of this function exactly equal to 0? So I have x1, x2 here. x2 should be equal to 0. So the function is 0 here, and it is actually going to be equal to 0 here at 2 pi minus 2 pi, etc. Okay? These are where this function is going to be exactly equal to 0. Okay? So what can I say about the properties of this function in terms of sign definiteness? Okay? So everywhere else the function is positive. Right? So in a small ball around the origin, if I get a sufficiently small ball around the origin, what can you say about the function value? What can you say about the sign definiteness? If I take a small ball around the origin, is the function going to be... First of all, I can ask you the following question. Is the function globally positive definite? Is the function globally positive definite? If it is globally positive definite, then it has to be larger than 0 everywhere other than the origin. This is the global positive definiteness. Okay? Is this function globally positive definite? No, it can take 0 values at other places than the origin. So it's not globally positive definite. Is it locally positive definite? So in a small ball around the origin, can I find a small ball around the origin in which the function satisfies this property everywhere except the origin? And yes, I can actually, if the radius of the ball is smaller than 2 pi, I will satisfy that property. So I know that V is locally positive definite in this case. Okay? This function has another property as well in terms of sign definiteness. We know that the function, so this is not satisfied, so the function is not globally positive definite. But do you think this is satisfied for all x larger than or equal to 0 for any x? Do you think this inequality is satisfied? Yes, this is satisfied. So what does this mean for the sign definiteness property of this function? It is at the same time what? It is globally positive semi-definite as well. Okay? So V of V is globally positive semi-definite as well. Okay? But here we won't be using it because for the Lyapunov's direct method, what is required to us is that the function should be locally positive definite, and this is going to be the property that we are using in order to be able to prove the stability of the equilibrium point. So now let us try to calculate what v dot is. V dot of x is equal to, I can actually take the derivative of this function, and the derivative of that function is with respect to x1 is going to be sine of x1 times x1 dot, which is x2. So I will multiply this by x2 plus derivative of that function with respect to x2, which is going to be x2 times x2 dot. Okay? So minus sine of x1 minus x2. Okay? So in that case, some terms are actually cancelled, and we get minus x2 squared. What is the property of this function? It is negative or zero, and it is going to be negative semi-definite, local or global. The function is this is going to be negative semi-definite because it can take zero values at other places than zero, than the origin. So this is going to be negative semi-definite. What about local property or global property? Is this true only in a small ball around the origin, or it's true everywhere in the state space? This is globally negative semi-definite. So this actually implies that it is at the same time locally negative semi-definite as well. Okay? So therefore here the conditions of the theorem are actually satisfied, which actually means that xc is equal to 0, 0 is stable in the sense of Lyapunov. So by using this Lyapunov function, we cannot say anything about the asymptotic stability of the equilibrium point. Okay? So unfortunately, this Lyapunov function did not allow us to say anything about the asymptotic stability of the equilibrium point. So using this function, no conclusion about the asymptotic stability of the equilibrium point. So when you use a Lyapunov function, and when you cannot get a conclusion about asymptotic stability, sometimes you can find other stronger Lyapunov functions which can result in stronger conclusions for the equilibrium point. So here, some people worked on another Lyapunov function, and it is the following for this system: 1/2 x1 plus x2 squared. This is something like this, plus twice 1 minus cosine. Okay? This is another Lyapunov function for the same system. Okay? I know that this is larger than or equal to 0, this is larger than or equal to 0, and this is larger than or equal to 0. Okay? If the function v of x is equal to 0, then all of these terms should be equal to 0. x2 is equal to 0, x1 plus x2 is equal to 0, and 1 minus and cosine x1 is equal to 1. Cosine x1 is equal to 1. What is the common solution of these equations? I need to solve these at the same time. Okay? If the function is equal to 0, all three equations should be satisfied. What is the solution of this equation? These equations at the same time.
Right.
x1 should be equal to 0, x2 is equal to 0. So we see that this function is only 0 at the origin. Okay? That is actually what we know in this case. So what is your conclusion about the sign definiteness of this function? It is. It is positive definite. Global or local? It is globally positive definite. Okay? In this case, that is what we know. Let us calculate V dot quickly. Sorry, I will. We can take the break afterward. So here I have. Let us calculate V dot. V dot is going to be derivative of this function with respect to x1 first. The derivative with respect to x1 is going to be x1 plus x2. That is, this thing with respect to x1 would give me x1 plus x2 plus 2 sine of x1. This is the derivative with respect to x1. I will multiply this by x1 dot, which is x2. And the derivative with respect to x2 is going to be x2 plus x1 plus x2. Okay? This is the derivative with respect to x2 times that second function. Minus sine x1 minus x2. So here let us distribute this thing is nothing but 2x2 plus x1. Let us try to distribute these terms. So I have x1 x2 plus x2 squared. I have plus 2 x2 sine of x1. Okay, and then I can actually write the four terms coming from this, and I will first write the sine related terms minus 2 x2 sine of x1, and I have minus x1 sine of x1. These are the sine related terms, and I will have also this minus x2 related terms as well. So minus 2 x2 squared and minus x1. Okay. x1, x2s are cancelled. These are gone. These are cross terms. These are indefinite terms, as you see. These terms are indefinite, and this term is also indefinite. Okay. So for our analysis, these terms should actually be cancelled. So these are cancelled, and what I get at the end is the following: V dot is equal to minus x1 sine of x1, and I have minus 2 x2 squared minus x2 squared. So what can you say about the sign definiteness of this function? So first of all, this term is smaller than or equal to 0. And can you say that this term is smaller than or equal to 0 all the time? X times sine x1. Sine can be negative, so this term can be positive actually. Okay? So this is not always smaller than or equal to 0. Okay? But what happens if I constrain myself into a small range for x1? If x1 range is very, very small, in that case, x1 times sine x1 is always going to be a positive function. Okay? So whatever property that I'm looking for here, it's not a global property. Because it's not a global property because this term can be actually positive. Okay? So minus x1 sine x1 can be actually positive. So here, when I look at the property, we don't have a global property, but we have a local property. So the function is locally negative semi-definite or negative definite. If the range that we are looking for, if it is very, very small, in that case, this function is only going to be equal to 0 at x1 is equal to 0. Okay, if x1 range is very, very small, this is going to be positive, but except for the origin. And this thing is also exactly equal to 0 at only the origin, and everywhere else it's going to be give me a negative term. So this is actually a locally negative definite function. Okay? So in a small ball around the origin, it is zero it's negative everywhere other than the origin. In a small ball around the origin. Okay? So this is locally negative definite. So by using this, we could actually conclude that xe is equal to 0, 0 is locally asymptotically stable in the sense of Lyapunov. Okay? That is, so sometimes one Lyapunov function might not be sufficient to prove something. Okay? So in that case, you can find other Lyapunov functions which can allow you to prove some stronger result than before. And this is the strongest result that we can get for the lower, for the downward equilibrium point of the pendulum. Let us give a break. We can meet back at 50 past 4. 50 geçe tekrar buluşuyoruz.